My name is Olaniwaju Charles. My research topic is the use of traditional machine learning models for water potability prediction. Introduction. Water quality or water potability prediction is crucial for safeguarding public health and environmental sustainability. Contaminated water poses significant risk, contributing to the transmission of diseases such as cholera, typhoid, diarrhea, hepatitis, and so on and so forth. Ensuring potable water remains a challenge due to the inadequate management of water resources, including the release of wastewater from urban areas, the industrial areas, and the agricultural areas. Challenges in ensuring potable water. Examining water potability traditionally involves collecting water samples from the source and conducting laboratory analysis on the samples collected, which is often inefficient, it is costly, and time-consuming. Consequently, there is a growing reliance on intelligent systems like machine learning for real-time monitoring. The overview of machine learning and its potential in water quality prediction. Machine learning involves programming software to learn from data and adjust its behavior accordingly, enabling pattern recognition and understanding of underlying data behaviors. Machine learning presents opportunities for evaluating. It helps to categorizing and forecasting water quality indicators, accurately replicating hydrological processes and contaminant transport with sufficient data. Now let's consider the objective of this study. This study exploits the application of traditional machine learning algorithm, which includes the logistic regression, the SVM, the support vector machine, the random forest, decision tree, nearest neighbor, and SG boost in predicting water potability based on the physiochemical properties that have been given in our data. The research aims to assess and compare the performance and accuracy of these algorithms for water quality prediction. The summary of previous research. Patel et al. Evaluated traditional machine learning models like the SG boost and random forest for predicting drinking water potability. And eventually, he discovered that the SG boost from their research demonstrates a superior performance. Nasri et al. Study assessed machine learning classifiers and staking assembles models for water quality classification using the water quality index with CAT boost, achieving the highest individual accuracy when compared with other assembled models that we actually used. Now, for this research, we want to consider the methodology overview. The first one is the data collection. From the data collection, we're moving to the data preprocessing, where the missing data were handled and the outliers were removed as well. Then the feature scaling, the standardization was actually done as well. The model training defaults. The model training was carried out using default and the hyperparameter trainings for the 6 algorithms, for the 6 models, I mean. And the performance metrics were evaluated using the confusion metrics, the accuracy, the precision, the recall, the F1 score, and the ROC. The methodology description. The first one is data collection. The data used, the potable water data set that was used were obtained from the cargo, and it is actually an unbalanced data set. The data preprocessing, The data were cleaned, checking for the duplicates, the missing, handling the missing values, and removing the outliers. The outliers were actually removed first before replacing the missing data with the mean value or the features of each features. I also performed feature selection as well. Now, the feature scaling, the Z-score normalization technique was carried out using the standard scaler, which is one of the skits, the scikit-learn library. The data splitting, it was 80-20, 80 for the training and the 20 for the testing. The model selection, as I mentioned earlier, were the 6 models I mentioned in my introduction. As well, the hyperparameter tuning was also carried out using the grid search CV for optimization. What are the challenges encountered? The first one is the computational challenges. The hyperparameter tuning, which involves finding the optimal set of parameters for each model, was a computational intensive process. And this actually led to slow execution time, as the tuning algorithm like the grid search CV can be resource intensive, especially when large data sets were actually used. And then oversampling limitation as well. Incorporating oversampled data using smooth into the model to address class imbalance resulted in a noticeable decline in performance. This actually made me to revert back to the original data set, which actually performed more better in terms of accuracy than when the data has been balanced using the smooth. And the feature selection effectiveness as well. I carried out the feature selection using the selecting k-best. The 5 best features were selected and were used in training those models. But I discovered that it was not optimally effective compared to when the all features, which is the 9 features given in the data set, if they were used. So that actually made me to drop that particular option and make use of all the features given in the data set. These are the results generated. The results after before the hyperparameter tuning using the default parameters. Then after using the result generated after the hyperparameter tuning using the grid search CV techniques. These are the best hyperparameters. Table 2 is showing the best hyperparameters for each models, as you can see from the table. And this is showing the confusion matrix for the random forest classifier. Why the graph here is actually showing the area under curve, the ROC, which is the receiver operating characteristics curve for the various models after the hyperparameter tuning. The result, the conclusion, the discussion and conclusion. The conclusion, ethics, and suggestion. For the conclusion, the study concludes that the random forest after hyperparameter tuning emerged as the best performing model with an accuracy of 0.72 and a competitive area under the curve value of 0.63. Its ensemble-based approach effectively captured complex data relationships, aligned with the previous research highlighting the effectiveness of assembled method like the random forest, the SVB boost, and the SVM in water quality prediction tags I mentioned earlier in the previous research. What are the professional, ethical, and legal considerations? It involves ensuring data policy, the security, fairness, transparency, accountability, responsible AI deployment, legal compliance, peer review, and stakeholder involvement to uphold integrity and responsible use of data and models. The suggestion for future research. These are the 4 suggestions for the future researches. Exploring advanced machine learning techniques such as the deep learning, assembled method, or hybrid models for enhanced predictive accuracy. Incorporate additional data source like the satellite imagery or meteorological data to provide a comprehensive understanding of water quality dynamics, and to also develop real-time monitoring system, leveraging the machine learning models for continuous assessment and proactive management of water resources, and foster collaboration between researchers and water authorities and stakeholders to facilitate knowledge sharing and standardization of methodologies. Thanks.